In this video, we will be going over some advanced exercises, meaning that we will tackle infinite data structures, I/O actions, and quick check. Okay, so just like the last two videos, at first I will give you a description of the exercise or the problem, and then I will give you the solution. Okay, so let's start. The first exercise will handle this data structure of a tree. This tree should not really be ordered in our case, but we want to look at trees that have tuples of integers inside them. Those integers correspond to how often you take the left or the right path. So if we look at the first left node, for example, it is 1, 0, because we went left once and, well, right no times. So then a 1, 1 node means that we took the left path one time and the right path one time. Okay, and we now want to look at a tree that is built this way but goes on forever. It has to be infinite. Now, since we cannot really evaluate such a tree without having some function like take for lists, we want to write a function called cut. Cut takes an integer and a tree and returns a tree. And it works like this. Imagine that this tree is t. In this case, cut 0 of t would just, well, leave us nothing and would leave us a leaf. Cut 1 of t would cut at the first height, cut 2 at the second, and cut 3 at the third. And now you understand how it would go on for 4, 5, and 6. Basically, we cut off the tree and every subtree at a certain height. Thus, cut will give us a finite tree even if we supply it an infinite tree. Okay. So now the exercise is create the function cut and the infinite tree as described. In my case, I called this tree inftub tree. Well, you can call it whatever you would like. Right. If you want to evaluate this tree, by the way, you can add a deriving show to the data type of the tree. Okay. So please try this exercise and pause the video now. Okay, so I'm assuming you have unpaused the video, so let's go over the solution, shall we? Okay, the tree is built similarly to how we build infinite lists. We have a helper function, aux in this case, that gets the initial tuple, which is 0, 0, and then it recursively builds new subtrees within the node constructor. Of course, a leaf constructor is never used since those subtrees are never ending. And what we do is we take the tuple we have at the point when aux is called, and we put that as the value of our current node, and then, well, again, just recursively go down to the subtrees, or the subtrees are built recursively with this helper function. Okay, so now let's look at how cut works. Cut, in this case, I have not checked whether n is smaller than 0, so maybe you can do this if you like. In my case, I just assume that the user will use the correct arguments. So, okay, if we are at the point where we cut 0, then the tree we have is irrelevant. We just return a leaf. And if we need to cut another height, so some positive n, but we are already at a leaf, there is nothing we can cut, so we return a leaf. The interesting part is when we actually have to cut something and we have some node. in this case, we return a new tree with the node with its value, and then we go down into the subtrees and we cut the subtrees because, of course, there is nothing else we can cut. And they will, hopefully, give us the correct tree. But yes, in this case, of course, it is correct. So maybe out of curiosity, let's look what a cut of our infinite tree would look like. Well, in this case, it is a bit, well, not the nicest output to look at, but we can see the pattern that we wanted. So we can see that the most outer node has the tuple 0, 0, and its subtrees have 0, 1, and 1, 0, and so on and so forth. Okay, so that's about it for our infinite tree. Exercise 2 is still working with the same data type, but now we want to look at trees that actually have ordered values. In this case, we want to use the ordering that we have in a binary tree. So the value of the node of the left subtree has to be smaller than the value in our current node, and the right node has to have a value bigger than our current node. So just the normal ordering for binary trees. And now we are concerned with a in-order traversal, meaning that we start at the most left leaf, and then we go up to the next value in this ordered sequence. So here you can see how this in-order traversal should work. And we are now concerned with two things. First of all, we want a function insert that inserts a ordered value into a tree, and then of course returns another tree that has this binary ordering. And then we want to construct a function called inOrder, which takes a tree and then returns a list with all the elements in a in-order traversal. So your task now is write the functions insert and in-order for the binary tree type, and then create a quick check property that checks if the in-order traversal of a tree built with the insert function is sorted. Now, there are some things you have to keep in mind and look out for when constructing this quick check property, but that is something you should think about. Another thing that I need to quickly mention is, since we want to call this function insert, if you import anything from data.list, you should hide the import of insert with hiding insert. In this case, you hide the definition of insert within data.list, so you can create your own insert function. Okay, so this is the exercise. Please do it now and pause the video. Okay, welcome back. So let's look at the solution. So inserting a value, of course, isn't too hard in this case. If we insert a value into a leaf, it is trivial what's happening. Of course, we just insert the value and have no subtrees. And if we have a node with a value, we simply compare this value to the current value and then either insert left or right. So this shouldn't be too hard. The in-order traversal also isn't that complicated. In-order traversal of a leaf obviously is the empty list. And if we have some elements, so if we have a node, we first do a in-order traversal of the left subtree, then we append this value, and then we append the in-order traversal of the right subtree. And if we do this recursively for every subtree, we get the in-order traversal. So those two functions are not that complicated. It is more complicated to construct the quick check property. So let's look at what you could come up with. Now, the problem here is that if we want to test insert and in order in one property, we have multiple ways of doing it. So in this case, what I do is the testing data actually is a list. In this case, a list of ints. If you're unsure why I use this types variable, you can go back to the quick check video where I described the problem of having not that well typed testing data. Okay, so what we check here is that the sorted list of XS equals XS prime, and XS prime is the in-order traversal of a tree which is built like this: fold R, insert, leave XS. So what's happening here? Well, insert actually works perfectly in a folding context, where the tree we spit out is the accumulator, and the value we want to insert is the element that fold provides from the list. So we start with a leaf, and then we insert all of the values into this binary tree. So of course, an in-order traversal of this tree, if our insert function works, should result in a sorted list. And that is precisely what this property is checking. So another way of writing this property could be by already supplying a tree that has a certain type and a value, and then checking if this tree right at the beginning is a sorted tree. So if the in-order traversal is sorted, then you check whether inserting into the tree still gives you a sorted list. You could do it that way, but the problem is that restricting yourself to trees that are already sorted will result in many tests being dropped. So it could take a while till this test is actually running through. So this property is a bit nicer and it just works a bit better. Of course, if you're unsure about the size of the lists that are being tested, you can always put some precondition in there that the length of XS needs to be bigger than a certain constant, for example. Okay, so now for the last exercise, we want to actually write a program which we compile on our computer and then run. So this time we don't just put stuff into GHCI, but we actually want to compile something. And the program we want to compile does the following. It asks the user to specify certain words that need to be searched. And here we see how I supply some of those words. And then it asks for a file to search these words in. And if it has found the words, it will say that the word has been found. And if it didn't find the word, it will say that it hasn't found the word. Okay, so let's go through it step by step so you understand what the program does. It first greets you with this output: specify the words to search. Then the user supplies the first word, and then maybe the second and the third and the fourth and the fifth. But now, if the user just doesn't input anything and hits enter, then the program knows that the user is done inputting words. So at this point, it asks for a file to search. Now, this should be relative to the path you are in at execution time, so relative to your current working directory. So if there is a lorem.text in the same folder as you are in right now, or the same directory, then it should search for these words within this text file. By the way, this lorem text file is in the description, so you can use it for testing. Now, the specification, or what we want to specify for this search, is that it is case insensitive. So, for example, this dolor wouldn't be in the lorem.txt if we were case sensitive, but we want to be case insensitive. And another important restriction on this program is that it should first tell you all the words it has found, and after that tell you what words have not been found. So this shouldn't be mixed. Okay. So since we want to write a program that we actually compile, we need a main IO action. This is not a main function like in other programs. No, this is a main IO action. So your program will start like this, where you write main equals do and then, well, something. Now, input-output will be done with system.io and the functions we have here. Read file, put string ln, and get line. Read file gets a relative file path. By the way, file path is just an alias for string. So this is nothing fancy. A file path really just is a string. You can check that in GHCI with :i file path. There it will tell you that file path is an alias. Okay, and read file then returns an IO string that has the file contents within it. Put string and put string ln, well, they put a string on standard output, and get line gets a line from standard input. One tip I have for you is to use this function right at the beginning of your program. hset buffering standard out no buffering. What does that mean? Well, imagine you have a put string line before a get line because you want to tell the user to input something. It could be that your program is buffering the output of this string and is waiting for user input before it actually writes this message to standard output. It might be that this isn't a problem for you, but for me it was. So in this case, you need to flush the output. You need to flush standard out. But a much more, well, simple solution is to set the buffering to no buffering. In this case, every output gets flushed immediately and we don't have any problems there. Okay. When we have written the program, in my case, I called the file task.hs, we can compile it with GHC. And then you should have three files, task.hi, task.o, which are irrelevant for us. And then you actually have the compiled task. This also depends on what system you are on and what GHC distribution you use. But on Linux, for example, you would just get the executable task. And then executing it again should have this behavior as a result. Okay, so this is the exercise. This is a bit of a bigger exercise, and it really gives you good training when it comes to IO actions. This is presumably, if you followed this course, your first program that you will compile. So this is something really exciting. At least I think so. Okay, so pause the video now and try this exercise. Okay, so let's look at the solution to exercise 3. So here is my solution for the main IO action. As we can see, I set the buffering to none. And here are some functions that that we will look at in a second. I just want to go over the rough outline of what this program does. So at first, it evaluates this IO action called get search words. Get search words does the whole thing with asking the user for search words and handling this empty input and stuff like this, right? And in the end, SWS will be a list of strings. That will be the list of all the search words. Okay, then it asks for the file to search and it gets the path with get line. After that, it reads from this path with read file. And then we have another function called find strings, which takes the search words and the text and finds the strings. So it really just returns a list of all the words that have been found. Then from this definition or from this result, we build this nfound list, which is just the difference of all the search words and the ones that we haven't found. So found are the words that have been found, and nfound are the ones that have not been found. And then we use this map m underscore. What that does, I will explain a bit later. It's just used for the output, but we're not concerned with that right now. We want to look at what getSearchWords is doing. So, getSearchWords, as I said, is an IO action returning a list of strings. In this case, we get the message, specify the words to search with put string line, and then we have this helper IO action, aux. So what it does is it prints the prompt and it gets the line. It checks if the line is empty, and in this case, it returns the empty list. If not, it gets the result that we get from a recursive call, so meaning from the next call that we have to aux, and then it returns the first line that we had with the rest of the input of the user. And thusly, we get all the search words in the correct order, actually. Okay. So now let's look at find strings, because that's the second function that is actually, well, interesting. As a helper function, I have written this lower function, which uses toLower from data.char. So this is very important. Every time you want to use a function from any module, you can use Hoogle, for example, to search for functions that you might not know. So when I prepared this exercise, I didn't know that toLower actually existed, and I found that out. Okay. And actually, I also use isLetter and isSpace also from the data.char module. Okay. So let's look at what those functions are doing. Lower is simply returning a string from a string just with lowered characters. Okay. Or with lowercase characters. Okay, so now find strings gets the search words and the text, and it does the following. It builds a new list from all the words from the search words, where the lower of W, so the lowercase version of the search word, is an element of text words. So, okay, let's look at what text words is. Text words is a mapping of lower to the words of ftext. Words is the function that splits a string on a space, meaning that it takes a string and it gives you a list of strings separated by spaces. Okay. But it doesn't call this function words on text, but on ftext. Now, what is that? Ftext is the filtered text, where I called filter with this little x to isLetterX or isSpaceX. Why is that the case? Well, we are only trying to search for words. We are not trying to search for punctuation, for example. And this could actually be a problem when calling the function words, since if we have something like lorem comma, then the word that we get out of this is lorem comma, not just lorem. So in this case, I just pre-filter everything that is not a space and not a letter. So in this case, I also filter numbers. However you want to filter it, you don't have to be as strict as I was. You can do it however you like. But in this case, we have the filter text that we can now pass to words. And then again, we lowercase all the words from this filter text, and then we can do the actual checking of our search words. Okay, so now we can go back to the whole thing, and now hopefully we understand what this program is doing. Get search words, does the prompting and gets all the search words, and find strings finds all the strings. The interesting thing might be what mapm underscore does. So mapm underscore has a interesting signature. So it works on a foldable T and a monad M. A foldable, in this case, is just a list. And well, the important thing is a monad M. So it takes a function a to monad B and a foldable TA, and then returns a monad of the empty tuple. Okay, so in our case, we have the following. Mapm underscore gets this function s to put string with some string as an output for all the words in the found list. And then we do this call again, but with a changed string, in this case with not found and with the nFound variable. So what does mapm underscore actually do? It goes through all the elements of the foldable, in this case our list, and it applies this IO action. So it could be that this is not an IO action, but some other monad. In this case, we wouldn't do a bind, right? So we don't do a bind here, but what we do is this anonymous bind that we had for the monads. So a binding where we drop the actual value that we get. And in this case, this is exactly what we want to do. We want to print all the words in found, right? So what we want to do is we want to print every single one of them, and what the actual end result of put string ln is irrelevant for us, since it is just an empty tuple. It is IO of the empty tuple, so we don't care for that at all. And we also, in our application of mapm underscore, we also throw that away, since we don't save the end result, which would be, again, just the empty tuple. So this is a neat way of going through all the elements in a list, for example, or any other foldable, and applying some anonymous bind with a monad to it. Well, I don't really know if this makes sense outside of I/O and networking maybe, but maybe there is some other usage for this.